Today we are going to discuss package formation. So, the package of the roving frame or speed frame is a roving bobbin. A sketch of the roving bobbin and image they are shown in this slide. If you look at the geometry of the package, what you see is this, that the bobbin has a cylindrical body at the center part and it has two tapered ends. So, the height is around 12 to 16 inch, that is the height over which the roving coils are laid. Then the diameter of the bobbin varies between 5.5 to 6.5 inch, we can convert them into centimeter, and the tapered angle varies between 85 to 95 degree. This is how the geometry of the bobbin can be described, and there is a bare bobbin on which we lay the coils of the roving. Typical roving bobbin size are shown here. It could be typically 12.5 inch to 5.5 inch, whereas 5.5 inch the diameter and 12.5 inch the overall height of the bobbin. So, there are various sizes which can be made on the machine. So, the maximum can go up to 16 inches in height and the diameter can go up to 6 inches, that is the maximum value as shown here. Now, we look at the formation of the roving bobbin. If that is the typical shape of the bobbin, how the roving bobbin needs to be formed. Roving is wound in the form of coils laid adjacent to each other on a bare bobbin, which is made of some plastic material. And we start from the bottom and you go up to the top. The laying process starts from the bottom of the bobbin and then we move up towards the top till the entire surface is covered. Thus, a layer is formed covering from bottom to top. The coils neither should overlap nor leave too much of space in between them for avoiding damage and maximum space utilizations. If you leave space between the coils, then the entire surface is not filled up. So, there will be loss of weight of material in the bobbin. Similarly, the coils should not ride on top of each other. They should not be so close to each other that they should not ride on each other. In that case, the coils may slip or the coils may get damaged also. And then after the formation of one layer, subsequent layers are laid on top of the previous layer. So, this is how we start. We start with the very first layer like here shown in this diagram, then we form the next layer. This side, right hand side is the cross sectional view and the left hand side of the diagram shows the surface view of the bobbin. From there, now the length of the bobbin surface filled with the roving is gradually reduced. So, the first layer, the length which is covered, it is the longest, and the subsequent layers will reduce their length. If we keep reducing that, then a tapered end will be formed. And why do you need this tapered end? Because it helps in avoiding coil slipping from the edges. If we do not have a tapered end, if we have a end like a cylinder, in that case from the edges, both on the top and the bottom edges, the coils can slip and that will create problem with the subsequent process and the roving also might get damaged, and therefore, we need a tapered end, and we create this by shortening the traverse gradually. Too high taper angle may cause roving coils to slip, and too low taper angle reduces roving content. So, therefore, we have to strike a balance between these two, neither too high nor too low. Each layer protects the layer below it from dust and flies as they are laid on top of each other. So, in a way, each layer is protecting the previous layer to some extent, because the previous layer is completely covered by the present layer, and thus we can say the layers are protecting each other. Now, the question comes, if this is the shape of the bobbin that we want to make, now how to wind the roving on the bobbin surface. So, let us look into it. Winding needs a relative motions between two elements. If we want to wind anything, a thread or a string or maybe a roving on any surface, we have to create a relative motion between two elements. One is the source of the roving supply, because in this case we are discussing about roving. So, it is between source of roving supply, which is the flare with pressure in the present case, and the other one is the package, that is the bobbin. Between these two we have to generate relative motions, a relative, in this case a rotational motion. In the case of roving winding, therefore, there are four possible ways to wind. What are those four ways? One is the bobbin rotates only, but the flyer remains stationary. The other alternative is flyer rotates only and the bobbin remains stationary. The third is both rotate in the same direction, but either bobbin or the flyer rotates faster than the other. And the fourth one is both rotate in opposite directions. So, theoretically, there are four different ways in which we will be able to wind the roving on the bobbin. Now, out of these four, which one we should choose and why? So, let us go to the very first one, that is the option 1 says bobbin rotates only, but the flyer remains stationary. Let us say the flyer is stationary and the bobbin only rotates. So, the diagram shows here there is a point B1 on the bobbin surface, and let us say the point P1 indicating the source of roving supply. These are the 2 points. Okay. So, on the left hand side at time t equal to 0, both B and P are exactly at the same locations, let us say, and now what is happening? Bobbin only rotates and the flyer does not rotate. So, after a time, let us say 1/4 revolution of the flyer goes to the position, no sorry, the flyer remains at the same position, bobbin rotates now, and therefore, the bobbin, the point B1 moves, or point B moves from B1 to B2, because bobbin has only rotated by 1/4 revolution. So, the earlier it was the location at time t equal to 0 was B1, now it has moved to B2, but the flyer or the pressure arm, you can say, that has not moved at all, because that is stationary. In this situation, what is going to happen? The roving is going to be wound 1/4 of the circumference as shown in the diagram by the orange line. So, if it rotates by 1/4 revolution, the roving would be wound by 1/4 circumference of the bobbin, and the flyer or the pressure arm is supplying the roving. So, it keeps supplying and the roving will be wound to 1/4 revolution. But in this case, winding will be possible, all right. From there we go to the next one, that is, in this case it is reverse, flyer rotates only and the bobbin remains stationary. So, at time t equal to 0, B and P are at the same location, the initial locations, and now at time t equal to t1, what happens that bobbin does not rotate at all. So, the B1 remains at the earlier locations, it does not change, but the flyer moves or the point P1 moves to P2. So, when the P1 moves to P2, that basically means that again in this case we will be able to wind how much 1/4 circumference of the bobbin will be covered by the roving as shown in the diagram. So, in the previous case and in the present case, in the both the situations we will be able to wind. Winding will not be a real problem in this case, both the cases it will be possible. But in the previous case there is only one problem, if I do not rotate the flyer we will not be able to generate twist in the roving. So, in a way we can say that the option 1 cannot be practiced even though we will be able to wind the material, we will not be able to generate any amount of twist into the roving. All right. And now from point 2 we go to option 3 now. In the option 3 it says that both bobbin and flyer rotate in the same directions. So, let both of them rotate in the same directions, we will be able to generate the relative motion between them, whether they rotate in the same directions or one of them remains stationary and the other rotate, relative motions will be generated in all the cases, except when both of them rotate in the same direction and at the same speed. If that is the situation, in that case there is no relative motion between them. So, in that situation we will not be able to wind anything if both of them turn in the same direction and at the same speed. In the present case they rotate in the same directions, but the speeds are not same. On the left hand side what is shown here, NB is greater than NF, bobbin speed is more than flyer speed, and we are showing here what is going to happen at time t equal to 0 and time t equal to t1. Both of them rotates, but bobbins rotates faster than the flyer. Now, that means the point B1 moves from B1 to B2, the point B moves from B1 location to B2 locations. At the same time the pressure arm also rotates how much, it moves from P1 to P2. Therefore, how much is wound, that is shown by the orange line. We can see that in 1/4 revolution of the bobbin we are still in a position to wind part of the roving on the bobbin surface. Okay. And you look at the right hand side picture now. In this case flyer speed is more than the bobbin speed and both of them are more than 0. So, in that case we can have a similar kind of diagram, but in this case what will happen, point B1 will move from B1 to B2, the bobbin is going to move from B1 to B2 and the pressure arm at that point, that is the roving releasing point, is going from P1 to P2, and therefore, we are going to wind a part of the roving on the bobbin surface. So, in both the cases we can see the roving has been wound how much, which has been wound to an extent on the surface of the bobbin which may be little less than 1/4 circumference of the bobbin, because both of them are moving in the same direction at different speeds. So, winding is possible in this case also. And the last option is when they rotate in opposite direction, this is also theoretically possible. So, these are the 4 options which are theoretically possible, and then we will check out of these 4 options which options we will ultimately follow. Now, in this case what we shown here, bobbin and flyer rotate in the opposite directions. Okay. So, if they rotate in opposite directions, so bobbin rotates in the anticlockwise directions. Therefore, B1 point goes to B2 as shown in the diagram, the pressure arm rotates in the clockwise directions. So, it has gone from here to there as shown in the diagram, let us say after a certain interval of time, and in this case this is the length which will be able to wind. So, bobbin and flyer both rotate, but in opposite directions and their speeds are not equal to same. The roving will be wound, which will be in that case much greater than the 1/4 circumference of the bobbin. So, in this case also your winding is possible, and because both of them are rotating, you will be able to generate some amount of twist. So, twisting as well as winding are still possible. Now, to understand if these are the 4 different options that we have through which we will be able to wind the roving on the bobbin surface, which one we are going to finally choose. We will try to now discuss this point. Let us first try to understand these 2 basic equations first. We call it winding equations and twisting equations. The twist equation says the twist is the ratio of speed of the flyer divided by delivery of the roving, delivery rate of the roving. So, it is T is Nf by V, all right. Our delivery rate is V and Nf is basically flyer speed. So, Nf by V, that becomes T, that is the twist, and the delivery rate has to be equal to winding rate, because whatever I am delivering per unit time, the same amount of roving has to be wound. So, winding rate and delivery rate has to be always equal. How much is the winding rate? Winding rate is winding speed into bobbin diameter into pi. So, and winding speed becomes the relative speed between bobbin and the flyer, that is the winding speed, into bobbin diameter into pi, and we can write it therefore, that this is pi dB into mod Nb minus Nf. This is what is the winding rate, and this must be equal to the delivery rate of the bobbin or roving, which is small v. So, small v should be actually equal to pi small dB mod Nb minus Nf. This equation should be always valid. So, winding rate and roving delivery rate, as discussed in the previous slide, is still being shown. Now, from there we can write that if Nb is greater than Nf, then I can write V is going to be pi dB Nb minus Nf. They should be equal, because winding rate is equal to delivery rate. From there I can write the Nb is going to be Nf plus V by pi dB, and therefore, Nb minus Nf is proportional to 1 upon dB. Why it is proportional to 1 upon dB? Because V is constant and pi is constant. Therefore, Nb minus Nf will be always inversely proportional to 1 upon dB. That means, winding speed should be always inversely proportional to the diameter of the bobbin. That means, as the diameter of the bobbin increases, the winding speed has to reduce. If I take the other alternative where flyer is leading, that is Nb is less than Nf, basically means in that case the equation becomes V is pi dB Nf minus Nb. You have to look at this, this is Nf minus Nb, in the previous case it was Nb minus Nf, this is the difference, and we can follow the same steps and say in this case Nf minus Nb should be proportional to 1 upon dB. So, in one case I say it is a flyer leading frame when flyer speed is more, in the other case we say it is a bobbin leading frame, bobbin speed is more. In both the cases, these are the fundamental equations which can guide us to actually decide how the winding speed has to be changed, so that we will be able to wind the roving properly on the surface of the bobbin. All right. From there we go to the next slide. Let us take a practical example to understand this point very clearly. Let us say typical twist that we need in a roving is typically 1 turns per inch, that is 39.4 or 40 turns per meter. Typically it could be plus minus 10% depending upon count of roving, type of fiber, because rovings are basically very lowly twisted material, since we have to draft them on ring spinning. So, we cannot put too much of twist. Roving delivery speed typically let us say on a machine around 20 meters per minute. Bare bobbin diameter assume let us say 3 inch, which is equal to 7.5 centimeter, and from there we can say this is equal to 0.075 meter. We can divide it by centimeter by 100 and we can write it will be 0.075 meter. Now, if these are the 3 practical values of twist, delivery speed and bobbin diameter that we choose, then speed of the flare that we need in order to generate 40 turns per meter is going to be Nf is going to be V into T, that is 20 into 40, it is around 800 rpm. I have to turn the flare at a speed of 800 rpm to generate 40 turns per meter if the delivery is 20 meters per minute. Next comes winding rate. The equation is stated here. Now, if the bobbin only rotates option 1 as we discussed earlier and the flare remains stationary, no twist will be inserted. So, even though we will be able to wind, but we have to discard this option because we will not be able to generate any twist. So, option 1 we discard, we go to option 2, that is flare rotates, but bobbin remains stationary. So, theoretically winding is possible, and because I am rotating the flare, I will be able to generate the twist also. Now, let us say in this case how much is going to be the Nb is 0. So, winding rate is going to be how much? If I put those values pi dB Nb minus Nf, so value of pi diameter of the bobbin and 0 minus 800, 800 is the speed of the flare. How much I am getting this value? Winding rate in this case is going to be 188.4 meters per minute. This winding rate is much greater than the delivery rate, which is only 20 meters per minute. So, there is a mismatch, that if I make the flare to rotate only keeping the bobbin stationary, then the winding rate is going to be much higher than the delivery rate, and therefore, this cannot be practiced as well. So, we need to reduce the winding rate, and this is only possible if we make both the flare and the bobbin to rotate in the same directions. We will say that if without rotating the bobbin, just rotating the fiber in one direction, if the rate is 180.4 meters per minute, and if I allow the bobbin to rotate in the opposite direction, it will cause winding rate to be greater than even 188.4 meters per minute. When bobbin speed is 0, it is 188.4 meters per minute. If the bobbin rotates in the opposite direction, it is going to be still larger, and therefore, which is basically option 4, and option 4 we have to also actually discard. So, we are left with the option where both bobbin and flare has to rotate, and they can rotate, and they have to rotate in the same directions. That is, either we can have Nb greater than Nf, but rotating in both clockwise directions, or if it is anti-clockwise, then both must rotate in the anti-clockwise directions. Or also we can have a situation where Nf can be greater than Nb, rotational direction has to be same. That means, out of these 4 options which are theoretically possible for winding, we will be ultimately going for option 3 only, and there either bobbin speed could be more than flyer speed or flyer speed also could be more than bobbin speed, both are possible. But we will see later on out of these two again which one we choose and why. Therefore, if we write the entire discussion in a table format, we can say in the first case bobbin rotates, but flyer remains stationary, no twist insertion, so we discard it. Second case, flyer rotates, but bobbin remains stationary, twist will be generated, but winding rate will be much higher than roving delivery rate, so we have to discard this. Option 4, both rotate in the opposite direction, twist will be generated, but winding rate will be much greater than delivery rate, so we have to discard number 4. And number 3, which is both rotate in same direction, but either bobbin or flyer rotate faster than the other, twist will be generated and the winding rate can be made equal to the roving delivery rate. Hence, we accept this particular option. Now, we come, as I said, that we have two options out of those. In the third option we have now two choices, we can say. One choice is bobbin is rotating faster than the flyer, the other choice is flyer is rotating faster than the bobbin. So, let us look at the first one, advantages of bobbin leading frame, that means the bobbin speed is more than the flyer speed. Point 1 is the motion transmission path from motor to flyer is much shorter than the bobbin. When we will discuss the gearing diagram or the drive part of the machine, then we will see that the motion transmission path from motor to flyer is shorter. So, the flyer starts rotating earlier than the bobbin when the machine is switched on. The bobbin starts with a delay, some delay. Therefore, for flyer leading frame, the roving will break near the pressure. Hence, bobbin leading is better, because flyer will start early, bobbin has not rotated, not yet started. So, bobbin speed is 0 at that moment, and hence the flyer starts, there will be suddenly high amount of winding speed, momentarily will be generated, but delivery is not going to be that much, and hence the roving is going to break. That possibility will be arising, and hence we prefer bobbin leading machines. The other reason is possibilities of roving sloughing off. This is shown in the diagram. Once the roving breaks, see, because during the manufacturing of the bobbin there is every possibility the roving might break due to some reason on some spindle. Once the roving breaks, unwinding of layers will start with leading flyer, because the roving will move against air resistance. So, look at this diagram on the right hand side, this is the case with flyer leading, and in this case the direction of rotation of the bobbin is in the anti-clockwise directions, and the broken end is shown here. And what will happen now, as soon as the roving breaks, the air resistance will unravel the roving from the surface of the bobbin. This is what is going to happen in this case, because the broken end is going against the air. So, the air will resist and will apply force on it because of the drag and hence the roving will start unraveling from the surface of the bobbin. That problem will arise. This will not happen in the case of bobbin. In the case of bobbin leading, if the roving end breaks, and see, let us say in this case the bobbin is turning in the anti-clockwise direction, the broken end is here, but this rotating in this direction. So, the resistance of the air is going to press the bobbin against the surface of the press the roving against the surface of the bobbin, and therefore, there is no scope for the roving to unravel. That is the advantage in the case of bobbin leading, and hence bobbin leading is also preferred. The other thing is, with the leading bobbin, the bobbin speed must be reduced slowly with increasing bobbin diameter. That is, with increasing mass of the bobbin, we have to reduce the speed of the bobbin. This is advantageous in terms of power consumptions also. On the other hand, with a leading spindle or flyer, the bobbin speed must gradually be increased. As the bobbin grows in diameter or grows in weight, we have to keep raising the speed in the case of flyers. So, that is, as the heavier mass, the speed has to be increased. That is the situation in the case of flyer leading frame. So, therefore, flyer leading frames are avoided and bobbin leading frames are preferred. Next is, what are the operations involved in building the bobbin. So, we have discussed the winding, different ways of winding and twisting. Now comes actual bobbin building. What are the various operations for building the bobbin? One is the traversing bobbin rail to fill up the bobbin surface. We must have a traversing bobbin rail. See, all the bobbins are actually placed on a big rail, and the rail keeps on moving up and down. So, the rail supports the bobbin, and the rail has to move up and down, so that the coils are laid on the surface of the bobbin, and we have to change the direction of traverse at the end of the upward and downward journey of the bobbin rail, because it has to go from bottom to top and then from top to bottom. So, as it reaches the topmost position, the direction of the traverse has to change. If it is going up, it has to be made going now down. So, there is a change in direction of movement, upward to downward, downward to upward continuously. Other thing that we have to do, we have to shorten the traverse length with each layer formation, as we discussed earlier, because we have to create a tapered end. So, the traverse length has to be reduced gradually. Then reduction in bobbing speed with increasing layer formations. As the bobbin diameter increases, winding speed has to go down, and therefore, bobbin speed has to be reduced, because the winding speed is the difference between bobbin speed and the flyer speed, or the flyer speed is constant, and therefore, to change the winding speed I have to reduce the bobbin speed. The other thing we have to do, changing the traverse rate of the bobbin rail. We have to change the velocity with which the bobbin rail is moving up and moving down. This velocity is also not constant, it has to change as the bobbin becomes bigger and bigger in diameter. So, these are the 5 different operations which are involved, and let us now discuss them. First, traverse of the bobbin rail. Roving needs to be laid over the full length of the bobbin, leaving a little portion from both ends for easy handling or gripping the bobbin. So, from the top maybe 1 centimeter, from the bottom 1 centimeter is not covered with roving bobbin, with roving. This is left bare, because we have to grip the roving for handling. Rest of the part is actually covered by roving. So, this can be achieved by reciprocating the laying point. If we want to fill up the the bobbin, the surface, bare bobbin surface, what we can do? We can reciprocate the laying point keeping bobbin fixed, or reciprocating the bobbin keeping laying point fixed. That means, either the supply point of the roving remain fixed and the bobbin moves up and down, or the other alternative is that the bobbin remain fixed in position, supply of the roving keeps on moving up and down. In both way, we will be able to actually lay the coils on the surface of the bobbin. Both are theoretically both are possible. The laying point, the pressure arm in this case are connected to the flyer is not moved, as it will change the angle of approach of the roving to the flyer top. That is why you have to remember, this is most important, that when both the options are there, either this or this, and I can reciprocate the bobbin rail or I can reciprocate the flyer. Which one I should choose? We choose the one where the bobbin rail moves up and down, but we do not allow the flyer to move up and down, because if I do this, then this is most important, the angle of approach of roving to the flyer is going to change, and that will affect my twisting, force twist generations, and can also affect the breakage behavior of the roving during the production of the roving bobbin. And therefore, we do not go for this and we choose the traverse of the bobbin rail. Next one is changing in direction of the traverse, is already told to you, as roving is laid from one end to the other and it goes to the other end, the direction of traverse has to be changed, so that only layers are laid on top of each other in the available space on the bobbin, and by laying the layers on top of each other, bobbin surface is utilized to increase the package content. So, that is how we do it, that is we have to change in the direction of the traverse. So, we go from one end to the other and then reverse the traverse. So, we form one layer and then we start filling up it again from the second layer on the top of the previous layer. So, thus we keep on generating layers after layers. Then we have to shorten the traverse length, because of we have to create a tapered edge. To create a conical bottom and top part of the bobbin, we have to keep on reducing, that as shown in the diagram, the traverse length is keeps on reducing, so that a tapered end is generated. This is required to ensure that the layer do not slough off from the edge during handling. How? By preponing the direction of changeover during each traverse. So, we have to, while the rail is moving up or down, so we have to prepone the time at which the rail is going to change its direction, that has to be also continuously changed with each and every layer formation. And bobbin speed has to be reduced. Why? Bobbin speed needs to be reduced as bobbin grows in diameter. It is needed to ensure delivery rate, which is constant, always matches the winding rate. So, if you look at this the equations, NB is going to be V by pi dB plus NF, and so the bobbin speed has two components. From here we can say one is NF, which is a constant component, the other one is this part, which is basically a variable component. NF is always constant, but pi dB, if you look at this, V is constant, is delivery rate, pi is constant, but dB is changing, because diameter of the bobbin is changing continuously, and hence we can say the bobbin speed has two components, one fixed component, constant component, and the other is variable component. So, we have to, as dB changes, the bobbin speed has to change. So, we have to have a mechanism to achieve this objective. And traverse rate of the bobbin rail also had to be changed. Why do you need to change the bobbin rail traverse? As the bobbin grows in diameter, the coil length, the length of roving for one complete winding around the bobbin, that is going to increase, because What is the length of a coil? It is the circumference of the bobbin. So, this is pi d b. Now, d b is not constant, as the layers are formed, d b keeps on increasing. So, pi d b is going to increase with the increasing bobbin diameter. So, we can say the coil length is not constant, but keeps on increasing as the bobbin diameter increases, and therefore, to lay one longer coil we have to give more time. And how do I give more time? This is only possible if we move the bobbin rail slowly. So, the bobbin rail needs to be moved progressively slowly. So, the traverse basically means traverse speed has to also reduce, and we will try to analyze this part here, relationship between traverse rate and bobbin diameter to the equation that we have already discussed earlier. Mathematically, this can be easily proved. Length of the coil is pi dB, length of roving delivered is V. So, number of coils to be wound per minute is always V by pi dB. Flare is stationary and the bobbin rail moves up and down. Flare's speed is stationary, it does not, is constant, whatever is the speed. Distance to be moved by the bobbin rail per minute is therefore is going to be n into diameter of the roving, n number of coils I have to create, and therefore, roughly we can say the distance by which I have to move the bobbin rail is going to be n into dr, and therefore, it is going to be V by pi dB into dr. Traverse rate of the bobbin rail V br is going to be therefore equal to V by pi dB into dr, and hence V br, that is traverse rate of the bobbin rail. Br stands for bobbin rail. So, velocity of the bobbin rail becomes 1 upon inversely proportional to the diameter of the bobbin, and hence mathematically we are proving that as the diameter of the bobbin increases, the velocity of the bobbin rail has to decrease. With this, we close this package formation part of the roving frame. Thank you.